Now we move. Okay, we move to our last talk. Our last talk is a plenary talk, and this is by Professor Marlan Scully. And first, I would like to thank Professor Marlan Scully to accepting our please someone help me our invitation. Okay, thank you very much. So his talk will be on using quantum mechanics to detect COVID-19 disease. But before that, Professor Scully, before that, I prepared a introduction for you. I would like to share the screen and introduce you. Is it okay for you?
Yeah, okay.
Okay.
So, Ahmed, thank you for inviting me. This looks like a fantastic conference. I'm sorry that I couldn't attend it. I am time sharing with the National Academy going on right now. And Dennis, I want you to come here and give your talk. And since everybody can give a talk everywhere, which means nowhere, we'll make sure that happens. I would like to give the talk that I prepared, but I want to stay within the 1 hour kind of limit, not the least reason of which is that there are other things that I have to attend to, but you guys are doing such great stuff in this symposium. Okay, so let's see if I can get my slides working for me. Where are we?
Okay, let me introduce Professor Scully, and Professor Marlan Scully is one of the founders of quantum optics. Actually, probably he's one of the toughest guys in this field. He's currently at Texas A&M University and shares a position with also affiliation with Princeton University. He's the director of Institute for Quantum Sciences and Texas Engineering Experiment Station, and he's a distinguished research chair. And he authored over 700 scientific articles. But I admire him is that he's 81 years old and he's conducting cutting-edge research. And this is his education background, and his MS and PhD is from Yale University, and afterwards, before that, he also went these universities, colleges, and this is his academic employment history. He worked in Yale University, MIT, University of Arizona, University of New Mexico, Max Planck Institute, Texas A&M, and Princeton University. And these are his selected honors. I don't want to read all of them one by one, but they are selected ones. So he built quantum optics groups at University of Arizona, College of Optical Sciences, to my remembrance, and University of New Mexico and Texas A&M University, where he's present at the present. He's best known for the first complete quantum theory of the laser, including also the photon statistics with Professor Willis Lamb, and quantum eraser and suppression of spontaneous emission with correlated emission laser, and using quantum coils to show theoretically and experimentally the first laser operation without inversion, lasing without inversion. Laser spectroscopy applied to anthrax detection, and he's also well known for his quantum optics and laser physics books. Actually, you should include many more to here. And this is his well-known book, the second well-known book, and this now he's also organizing physics of quantum electronics, and constantly in Snowbird, and they organized the 5th physics of PQE meeting last year. 50th, sorry. And this is, he's also giving the prize for the, I'm so sorry, I cannot, the prize for the Willis Lamp Award. And in this place, we can see him with Ali Yavan, Paul Mandel, Lamp, and Olga Kosharovskaya. And here we also see him with Glover. Okay, this is my introduction, and let me stop my share, and please kindly you can start your talk, sir.
Well, thank you, Mohammed. That's a nice introduction, and I'm looking forward to seeing you in person sometime soon. What I would like to do today is to give the talk that I've prepared, but unfortunately, it's really 2 talks. The first is a talk entitled Detection of COVID-19 Disease, and the second talk focuses on the old idea of Penrose. You know, he got the Nobel Prize for General Relativity this year, but he has interesting ideas on the ways in which he hypothesized quantum coherence within microtubules in the brain. And recently we've done some theoretical work on that, which shows that it's not completely ruled out by ultra-fast decoherence times. So I'll touch on that, but probably I'll give most of the talk on the experiments we've been doing, which are typified by the pictures here, experiments at Texas A&M and at Baylor, where we're doing the ultra-fast spectroscopy. The cover article in recent American Chemical Society Photonics shows the sequencing of DNA by tip-enhanced Raman. Now, you know that the tips are on the order of 40 nanometers, and the wavelength of light is, you know, what, 500 nanometers. Well, we have to be able to tell the nucleotide molecules apart at distances on the order of what, half a nanometer. And it works. And that's one of the few times when nature is kind to us and gave us much more than we expected. So I'll tell you about that, all of which goes within the context of the COVID problem and tracing out the amino acids on the surface of a virus. And so I'm going to tell you about these 2 things, but I'm going to do it in a historical context, namely, remind myself in your presence. Okay, come on. This is a new computer. I've got, we hear you. Well, I don't know what's going on here. Oh.
So you cannot change the page?
Yeah, that seems to be the case. I'll get it, just a sec here. I got a new computer. I lost my secretary, and we have a new president of the university. I'm dead meat. And this computer, I'm sorry, let me just keep talking, but I'll call my computer, call the guy who owns this computer and get him in here to help us. The point being that I want to review the work that we did over the years in anthrax detection. You remember that the anthrax molecules were sought by many people using different techniques 20 years ago after the anthrax murders. Hello? Excuse me a sec. Advance. Look. Okay. So, don't go away. This is Dr. Yi, who's my friend and colleague and whose computer I'm using. So the point is, 2001, the anthrax murders at Princeton were taking place, and we wanted to know how to detect this anthrax, weaponized anthrax in an envelope. And so that was not just a hot problem, but an important problem. And so we started working at A&M, came up with a technique we thought would work, but it utilized femtosecond pulse technology. Back in that day, in 2001 and 2, there were only a few universities that had that, Michigan and Princeton being the tops. So we made a collaboration with Princeton. I called them up and asked them if I could come and join them and use their lasers. And they said, well, if I took a position as visiting professor, I could. So we did, and that's what I'm going to tell you about first. Let me again remind myself in your presence of some things about the anthrax endospore that I assume you're not spending a lot of time thinking about, but it's a fascinating system. This view graph comes from one of our graduate students, Dmitry Pestov. I've stolen this from him, but the material comes from an early Proceedings of the National Academy article entitled Fast Cars. What do you mean fast cars? Well, we'll come to that in a moment. But first, let's go to slow anthrax. The anthrax endospore is a well-known from antiquity system. In the King James Version of the Bible, they talk about the plague that was visited on the Pharaoh. And it says in a footnote, this plague was probably anthrax. They piled the frogs up and burnt them, and it went into the air, and anthrax was everywhere. The fact is that the Greek literature details what is certainly the manifestation of anthrax, namely, for the same reason that anthracite coal is black, it's called Bacillus anthracis, because when a person is infected with this terrible disease, the molecules and atoms within the context of the cell put out poisons, toxins that dissolve the microcapillaries, and the person bleeds to death internally, turning black. The parasite, which is essentially what it is, constitutes about 30% of the body weight when the host is finally killed. And the way in which the system propagates itself is different than the usual parasite host system. It eats until there's a clear indication that there's not enough food around, no more nitrogen, carbon, and such. And it begins to build little lifeboats, little endospores within the cell. And they look like this. They're about 10 microns in size, slightly elliptical. There's a horny outside coating, but inside is where the good stuff is. This is a salt, calcium dipicolinate, and it contains all the protein and the DNA necessary for an endospore to come back, infect a new host, and start multiplying. let's see, what else would I like to say? Yeah, so this 17% by weight is calcium dipicolinate. It's a simple molecule. Think pyridine, which is of course just benzene with nitrogen replacing the carbon, and carboxylic acid out here at the side, COOH, two of them. You knock off the hydrogen, put on a calcium dipicolinate, and that's the salt that protects all of the ingredients, the protein and such, necessary for starting the new bacillus bacteria. Oh, so the way in which this is accomplished is of course known to everyone. An animal eats some dust around a century-old site and ingests these endospores. It takes about 10 to the 4 endospores for a lethal dose. If you get a few hundred, the body can fight it off. But 10 to the 4, which is what they weaponize these clumps to be in size, at 10 to the 4, the body can no longer fight off the toxins, and the spore wins out, unfortunately. Now, this marker molecule was investigated from a Raman point of view by Tom Spiro, one of my colleagues at Princeton. And Tom, back in the 70s, was able to spot anthrax by looking with ordinary Raman techniques. But unfortunately, it takes about 5 minutes. Well, it takes some minutes for a signal to build up. Of course, we'll come to that in a moment, but the Raman signal is very weak. And so we were looking at the advisability of using coherent Raman, coherent anti-Stokes Raman. And that didn't quite work, but a variation does. And so let me skip ahead now and remind you of Raman scattering, since some of the students might not have thought about that in recent times. Remember that your friend and mine, Adolf Schmeckel, 1923, before quantum mechanics, before de Broglie and Schrödinger, predicted the scattering event, which is now known as the Raman effect. Even though Mandelstam and Landsberg had it at exactly the same time, it became known as the Raman effect. Raman, a brilliant physicist in India, actually bought his ticket to Sweden before the prize was announced, because that's how long it took to get to Sweden. So another thing to learn from all this is that theory is always 5 years out from experiment. Predict something, and you have to wait about 5 years to get the experiment done. As a semi even-handed theorist, experimental enthusiast, I appreciate that with tongue in cheek, but never forget how valuable, how useful, how practical a good theory is. And I think that Schmeckel, knowing the Heisenberg-Kramers theory of index of refraction type physics, was able to go a long way. Now let's remind ourselves in the next few graphs what actually is going on. So we take a carbon monoxide molecule as an example, and we shine a laser on it with a frequency nu, and let's imagine that this carbon is a light molecule and oxygen is very heavy. It oscillates, the carbon oscillates. The oxygen is like a stone wall, pretend, And so in comes the laser light and backscatters off this reflecting surface. Let's think of it as a mirror. So we'll see upshifted and downshifted light, just like Doppler physics. And the backscattered Rayleigh light comes back at the same frequency that we sent in. A very weak signal then at the downshifted Stokes frequency is observed, and anti-Stokes is in principle observed as well. Now, Stokes is the usual result of any Raman experiment. Anti-Stokes comes in a minute, but remember back in the 19th century, all light that was scattered was redshifted, all in quotes, 90%. And Stokes was one of the guys who really taught us a lot about that. But we want to go on now to see if we can do something which is more than just this spontaneous emission. In particular, let's skip ahead now to coherent Raman scattering. Over on the lower left-hand side, we depict ordinary Raman, okay? So the pump goes in and the detuned transition involves Stokes radiation when we go from the ground state to the first excited state of the harmonic oscillator constituting our molecular spacing. Here, I want to go through a little bit of back of the envelope calculation, and I want to think about the physics with you, because when I first started thinking about this anthrax problem 20 some years ago, I hadn't thought much about Raman, and it became clear that this weak signal, 1 photon of Stokes for every 10 to the 10 photons of pump, is not going to work. So one thinks about other things that we might do. And because we were working on lasing without inversion and electromagnetically induced transparency, slow light, in which coherence is involved, many atom coherence, I wondered if I couldn't use some kind of a coherence effect, not properly appreciating at that time that that's exactly what cars is. I wondered if I couldn't use that. So I called up my friend Ron Shen, the guy who wrote a beautiful book on nonlinear optics. And I said, hey, Ron, how much of a payoff do I get for going to coherent Raman? And he said, look, you're the guy who works on all these coherence effects. You tell me. Excellent answer, because then I thought, oh, okay, I have a license to go spend time on this. Otherwise, I just go find the textbook. So here's how you think about it. Imagine, first of all, that we write the wave function for the molecule thought of as a simple harmonic oscillator with mass determined by the carbon and the oxygen, fair enough. So let's write the nuclear wave function, that is to say, the wave function which describes the position of these two atoms within the molecule, R being the spacing, as some probability amplitude B with a frequency term times the state vector wave function for the first excited state, Hermite polynomial H1, plus some probability amplitude for being in the ground state C, and the Gaussian Hermite wave function, and which again, capital R is the spacing between the two. So let's look at time t equals 0 with equal population in these two states. B and C is 1 over the square root of 2. So this is the probability amplitude characterizing the separation. Little r is capital R. And here is the same plot for the ground state. Add the two up at t equals 0, and you get the left-hand side preponderance, which is to say a compressed spring. Half a cycle later, when T is equal to pi divided by omega, you get a -1 multiplying this wave function, and you enhance the probability amplitude on the other side, so the spring is stretched. So you're seeing an oscillating molecule characterized in the usual way that we all know and love by such a coherent wave function. And that is, of course, characterized by off-diagonal elements of the density matrix between these two levels. Okay, so incoherent ordinary Raman absorb a photon, and one time in 10 to the 10, you get a Stokes photon. Coherent Raman, you send in laser light between a green and a red, and it drives this ground state coherence dynamically. It's like as if you have some kind of infrared field driving this transition, but for various reasons, selection rules and quantum mechanics, it turns out that it's sometimes possible to set the molecular system in oscillation using Raman, and sometimes using just good old infrared absorption. But if you want to do Raman detection, then this is the right way to go. And this coherent oscillation between B and C is then followed by an absorption. Now, if I want to do anti-Stokes, I'm going to start here and have the pump photon taking me up to some high-lying virtual state, and then I decay back down to the ground state, bam, and I get a blue shifted photon. That's anti-Stokes. But let's talk about scissors. Let's talk about just coherent Stokes radiation, because that's easier to look at the mathematics on. So create the coherence. Take a pump now, which may or may not be the same as this laser, and send it in, drive up to some virtual state, and get a correlated Stokes photon out. And this is not stimulated emission. This is coherent, spontaneous scattering from one point of view, and I'll come to that in just a moment. But how to answer the question, what's the payoff? Give me a back of the envelope calculation, or tell me at least what calculations are worth looking at. So let's just sum over all the molecules with a phenomenological matrix element, capital G, characterizing, of course, this process, and creating the, making this transition with the matrix element involving the usual Lorentzian denominators and matrix element squared. So the operator, which takes me from C to B, is then associated with the annihilation of a pump, the creation of a Stokes, and a phase matching term known to all of us these days. So how do you do a back of the envelope calculation quickly? Heisenberg picture. Put in the Hamiltonian we just looked at, calculate the operator corresponding to the Stokes field, assume a short pulse, and just multiply by tau, and you've got what you want. You've got the operator at time tau. Let's use that to calculate the number of Stokes photons. Put it in, square it up, A dagger A, do a little arithmetic, sum over the molecules, and lo and behold, you get two terms. A spontaneous term. This is pollen time in Texas, not COVID time. I've had all my shots, and we're in great shape here in Texas. Spontaneous, incoherent, one molecule, one atom physics, one photon 10 to the 10. Cooperative, many atom, coherent in a many atom sense, in an entanglement sense, as you'll see in a second. Looks like this, and I have the product now of the off-diagonal matrix characterizing coherence. And that gives me, the bottom line, the ratio of coherent to incoherent scattering, which is in all reasonable ways of talking about it, cooperative spontaneous emission, more like Dickey than stimulated emission. But it's coherent in the sense of the word that you usually think of Dickey superradiance as well. So here's the answer. We see then that the density comes in, the wavelength squared. Aha. Photon, how big is a photon? Lambda squared. R, capital R here, is the size of the cloud that I'm looking at. This is not the spacing between molecules. That's all contained here in the coherence, rho BC squared. So, okay, I can plug numbers in and find that I get many orders of magnitude enhancement by going from the incoherent to the coherent. And so it's also highly directional. We did experiments and showed that we get, indeed, many orders of magnitude enhancement, where rho BC, maximum is 1/2, of course, about 1%, and comparing it to what we calculate theoretically gives us a lot of encouragement for continuing with this line of endeavor. That is to say, let's use cars to detect anthrax. Well, I went to DARPA, made the presentation, and they didn't believe it. And of course, in retrospect, you all know why. They say, well, you're going to have a kind of background noise that's going to swamp you. And I convinced them that wasn't the case. So they said, all right, here's $1 million. Go show us why it doesn't work. So we went home and showed why it seems to work. And so then they gave us much more. And they said, now go do the experiment. So that's where we really got involved with our colleagues at Princeton. Oh, wonderful, fun time. And ended up with a paper in Science showing how it is that we can overcome the usual killer in cars. Remember what that is. If you're generating an oscillating dipole, oscillating molecular oscillation between B and C, not just two atom, but many atom, this then provides a driven oscillator off of which you scatter. But driven oscillators always go at the driving frequency between these two lasers. So it doesn't matter if you're scattering off of CO or SO or whatever. You have different ground state spacings for these two different molecules, to be sure. But the light scattered at frequency nu sub 4 will always be the same, because the oscillation of this molecule is going to be the driving frequency. That's the bad news. The good news is we can get away from that by doing fast cars. And let's not go there. Let's just say, suppose you start this oscillation. Now you turn off these two lasers. The detuned molecular system will adiabatically follow the driving field, and you'll be left with the molecule back in the ground state. But if you resonate when you turn off the driving configuration, you'll be left in a coherent superposition. Works. And with an eye on the clock, I'm not going to go through much detail here, except to show what the utilization of femtosecond techniques gives us. I think we're okay now. Come back in a bit, okay? So I think the computer is working. Let's keep trying. So ordinary cars, right, would give you a signal like this in our experiments. And we're looking at calcium dipicolinate, 17 more or less atoms, fairly simple structure. And if you look at driving frequencies on the order of 730, you get this. If you go 722, you get something that's kind of a mess, but still discernible from that. But now if you use a adaptive spectroscopic technique in which you, first of all, create the pulses just right, and then turn them on and off at just the right times, you go from cars to this femtosecond adaptive technique, which gives you a very nice sharp signal. And that's the business of fast cars. So with that, I'll move ahead and tell you about what happened. Let's see, I should go back and give you a little bit of the story here. So we worked at Princeton for a couple of years. Great lab there. A lot of fun in the chemistry department. But we never were able to quite make it work. But by that time, we had our own femtosecond lasers here in Texas. So I came home, teamed up with Alexei Sokolov and a few others, and we had it in short order. So that this kind of cars, hybrid fast cars technique is what we're extending in this next view graph. We began looking at other ways to enhance the Raman signal. And one very popular way of enhancing Raman scattering is by using surface enhanced Raman. You remember that if you look at certain features on the surface, you have roughness and you can get a kind of focusing of the laser field. You also get some enhanced molecular sensitivity because of the matrix elements being enhanced. And so that is surface enhanced Raman, a wonderful technique that's been around for some years. Well, what we started wondering is how about using surface enhanced Raman with cars? And for various reasons, you might not think that would be a good idea, but it turns out to be a good idea. And we were able to get many orders of magnitude enhanced signal over the surface enhancement, okay? And we were happy about that. There was a nice review article that came out some 5 years ago in which they talked about using, they talked about this result of Sokolov and coworkers, and they noted that you get an enhancement which provides astonishing sensitivity. And it does, and this is the article to look at. But now, moving on, we come to the anthrax business made into a problem identifying the COVID-19 virus. A much more challenging problem, of course. A virus bacteria is micron size, 10 microns. A virus is maybe 10 nanometers. Here in this picture, this virus is the virus that is associated with bacterial phage studies. And this virus is the virus which is associated with Spanish influenza, with the 1918 influenza. So what we're doing here with Volker Decker from Jena, who spends his time sharing between A&M and Germany, and he, my a bright young colleague who's working with us on this and other things, what we did was to do surface enhanced ramen, but using a tip instead of surface. So as I mentioned at the beginning, here we have a tip with the structure on the tip on the order of 15 nanometers in size, and light scattering off that hot spot. Now, I mean by that, the hot spot, so here's something which, I don't know, maybe it's gold, maybe it's silicon. In this case, we'll not worry about the exact material, but what we find is that by scanning the surface of a virus and doing surface enhanced or tip enhanced ramen, you're able to tell the difference between this virus and the virus which is used in these bacterial phage studies. Remember, this virus gets into the E. coli bacteria and kills the bacteria, and that's about the size of it. So here's the spectrum from these two viral ingredients. And you can tell that indeed it's quite different. And due to Volker and his colleagues in Jena, we were able to envision using a kind of fast cars in this context, going beyond tip-enhanced cars. And Volker suggested this should be called enhanced resolution fast cars. Fast enhanced resolution, faster cars. So with tongue in cheek, that's Volker's amusing designation. Well, it works. And Jürgen Popp and other of the great guys in Jena are the ones who get the credit for developing this technology. But Volker came with us after PQE last year, he was 2 years ago, 2020, and couldn't leave because by February of 2020, we had a lockdown from COVID. And so he worked with us here, and we enjoyed and profited from his presence. And bright young graduate student, Dr. Heeb, showed how he could, working with colleagues at Baylor and here at A&M and Rensselaer Polytech and other places, he could use this tip-enhanced technology to scan out the nucleotide bases in a DNA sample or an RNA sample, single-stranded DNA or RNA. That's amazing. So now here we're seeing single resolution, single nucleotide resolution, 0.5 nanometer. How can that be? Well, it's because of the structure on the tip of this tip-enhanced ramen culprit. So it's very exciting, and we can, and indeed our German colleagues are very active in tracing out the amino acids on the surface of a virus. And that's one of the things that we're focusing on right now. So there's a lot to do. This is very, very tricky science, but it's much more physics and optics than it is biophysics at this level. Certainly the biophysics is challenging and really wonderful that our biophysics colleagues can do what they do, our biochemistry colleagues. I heard a talk recently from the president of the American Cancer Society, and he said the next breakthrough in cancer is coming from physicists, not from biologists. And what he had in mind was being able to image and study single cells and single viral particles. So we're on the way, and I encourage you all to keep track of this stuff. If you look in this month's Physics Today, there's a beautiful picture of a cell covered with COVID-19 virus particles. Amazing, amazing. So now moving on. So moving on from the experimental coherent Raman, I've still got 15 minutes. I'd like to come to a problem which...
Sir, I'm sorry. Actually, you don't have time limitation. Please go on, and please, if you need, please just rest your voice.
Okay, can you say that again, please? I'm not hearing you very well. Are
Okay,
you hearing?
you don't have any time limitation, and if you need, we can wait. So you can also rest your voice if you need.
Okay. So is that better?
No. If you need it, you can make your voice rest. So, and we can wait. So no problem for us. And I would like to kindly tell that you don't have any time limitation.
Okay. Thank you very much. My limitation comes from the other end. I've got an obligation here at the Academy meeting. So
Okay.
I got to talk with those guys. I'm really thrilled with your conference. It's great. I wish that I could be here the whole time. Why don't we do this? Let me go ahead and finish this presentation. Now I'm going to get Yi on board to answer any questions about the previous material. He's an expert on the previous material. He's not involved with this microtubule stuff. And so let me present this, and we'll continue in the discussion with my young colleagues filling in here. Is that okay?
Yes, sir.
Okay. So again, I move ahead now to a more or less strictly theoretical program, although with Yakovlev and others, we are looking at experiments relevant to this issue. And you remember that there's a book called The Emperor's New Clothes, in which Penrose suggested that maybe coherence exists in the brain, and maybe the brain is a quantum computer. Well, that is amusing, and it's an interesting thought, but come more to earth and ask a simpler question. Can I see coherence effects in the context of these microtubules? And that's what Agarwal, Merkimall, Anatoly Shvydzinski, and Vlad and I have been working on. Now, the idea of coherence in biological systems is an ancient concept. It goes back to Froelich. Froelich may not even be known to some of you young people, but certainly was known to me in the days when I was working on superconductivity. Froelich is the guy who emphasized the importance of the electron-phonon interaction long before BEC, and really laid an important cornerstone down. Well, in about the same 10 years after BCS, BCS was 1957, Froelich was applying his energies to quantum effects in a biological system. And he made an interesting observation that maybe there's a vibrational energy which operates in proteins like Bose condensation. So most of his life, the laser business was not a big deal, but in his Excuse me. In his thinking, Bose-Einstein condensation was the paradigm, was the thing to keep in mind. And these days we know that he's essentially right. Well, a year or so ago, Zidong Zhang, Girish Agarwal, and I started looking at this old Froelich paper and began using quantum theory of the laser quantum Bose condensation ideas to see what we could do with the Froelich supposition, and then clear on back to the question of microtubules. Back at the heydays of Bose condensation in quantum gases, they looked at the way in which the laser phase transition analogy could be applied to a semi-rigorous calculation of N bosons, and found that indeed it's really true that the photon statistics of a laser and the atom statistics of a Bose condensate are not similar, they're identical. So that there's an analogy between the laser and maser and Bose condensation, and it's that point of view that we should bring to thinking about Froelich's interesting supposition and hypothesis. Now, what we are thinking about is perhaps best summarized in a couple of papers of recent times, some of it older than others, but in 2011, Dmitry Nanopoulos here at Texas A&M and his colleagues in London and at CERN started reviewing this topic of quantum mechanics in the brain or in microtubules. And they were thinking of the microtubules as constituting a kind of boundary condition that gave them a license to approach this problem as a quantum electrodynamical cavity. Well, maybe, maybe not, but it's interesting. And about 5 years before that, 10 years before that, a interesting paper occurred in which people were looking at these microtubules and hypothesizing that laser-like superradiance might be coming in. Well, at this point, it wasn't clear to them what's the difference between laser and superradiance. By the way, the answer is laser is coherent in the way that we all know it, obeys a coherent state, and is associated with atoms which are oscillating in phase. Superradiance, not so much. Superradiance is a collective spontaneous emission, but there's no coherence in a superradiant ensemble. And so we started looking at this problem from the point of view of doing a careful theoretical analysis of the superradiance in microtubules. And along about that time came a neat paper from our colleagues in Mexico and in Europe. And their paper, published in 2019 in the New Journal of Physics, they analyzed the superradiant characteristics of an ensemble of two-level atoms, wound two-level systems, okay, thinking of molecules, of course, wound in a coil like this. And they looked at the Dickey problem in a rigorous, quote unquote, a model. Here's a model, but within the context of this model, they did a great job of doing a numerical study trying to characterize the rate at which molecular emission, remember in Dickey superradiance, is many times faster than an individual atom or molecule will radiate in free space. Point being then that in this configuration, okay? So our young friends here do the calculation and they find that they get a bunch of eigenvalues where this is kind of like the effective spacing of the two-level system, but the spacing changes because you've got Lamb shift kind of physics coming in. You're seeing vacuum fluctuation and collective Lamb shift physics coming in. So along here, think about the frequency along the x-axis. This is the frequency of the effective two-level system, and this is the decay rate in units of an atom molecule in free space. So here we see something which is decaying at hundreds of times faster than the spontaneous emission rate. Well, that's interesting, right? Going from one spiral to 10 spirals, going from one atom to many atoms. So this is 2019, when I'd like to say we found this, but actually it was our contract monitor in Washington who found it and called me up and said, hey, what about this paper? So we went and looked at it and said, yeah, that's neat. We'll go put it in the context of what we've been doing analytically, and I'll skip to our work on superradiance over the past 10, 15 years. So the stimulus for what we've been doing, and this will tie back into the tubules, microtubule idea, involves looking at a Dickey state, and think first of all just Dickey. Remember, Dickey was talking about microwaves. So the wavelength was huge compared to the size of his sample. His sample is about a centimeter on the side, and the wavelength is like a football field, right? So all of his atoms are at the same place, so to speak. All of his nuclei are at the same place. And so he doesn't have to worry about any complicated phase factors. But now, these days, we do superradiance experiments in which the size of the sample is, again, a centimeter, but now wavelength is a micron, 10 to the minus 4 centimeters. So you get many, many wavelengths over here, many, many wavelengths across the sample. And so the size of the sample is much larger than the wavelength. And this is something that I was challenged by Steve Harris, who asked an interesting question. He said, can I have phase matching at the single photon level? So I thought, well, let me look into Dickey superradiance at the single photon level. So suppose you have N atoms, capital N atoms, and suppose that you send in a pulse, short femtosecond pulse, if you will, and it crosses the sample and excites, remember, it's just one photon, so it excites this or that, but only one of them. But it excites it in accordance with the dipole Hamiltonian. K0 is the wave vector of the incident photon, and R sub I, 1, 2, is the coordinate of the first, second, third, and so forth atom. So this is the Dickey state, which is timed. It's easy to think about this, multiply by C and divide by C, then I have omega times the time delay between the moment when I come in and the moment when I exit. Okay, So I see I'm running out of time, but I'm going to take another 10 minutes. And oh boy, I got to speed up a little bit. So what happens is that you excite this sticky state. You've got one photon excitation, but you don't know which atom it is. Oh boy. Oh boy. Okay. So we have now a interesting problem. So here's the wavelength being small compared to the size of the sample. And the radiation now is in the K0 direction, all right? And in fact, this is a log scale, so it's very strongly peaked in the forward direction. But this is a many atom, one photon problem. Look over here, cavity QED. I have many photons in the cavity, but one atom. And if I look at the ring down of that one atom, many photon problem, I see that it looks like this. Okay, this is Serge Hero's Herbert Walter physics. Come up here. What happens, amazingly, is that with this problem, cloud of capital N atoms, I get a probability of being in the excited state, that is to say, the state in which there is one atom excited in this cloud, or if you will, one photon in the cloud, swapping back and forth between the atoms, as compared to the problem of a single atom absorbing and emitting radiation. So the probability of atomic excitation goes like the matrix element of the atom times the electric field per photon, epsilon 0 being the MKS derivative, MKS permittivity. V is the volume of my cavity, volume of the photon, but everything is multiplied by the square root of the number of photons, of course, the time. Note that the important parameters are the volume of the cavity, photonic cavity, and the number of photons. Now we work out this same problem over a series of papers, and we find that the superradiant system, lo and behold, has exactly the same structure, except that instead of the number of photons, you got the number of atoms. Instead of the volume of the photon, you've got the volume containing the atoms. Oh, that's intriguing to my mind to see this kind of superradiant physics and this kind of radiative single atom maser as opposed to single photon superradiance. Now, move on to another question. Let's see, let me slow down for a second and note that, okay, you've got many atom physics coming in, and you're going to find that the emission of that photon that you're working with is much, much enhanced relative to the free molecule or atom. Well, if the spontaneous emission rate is enhanced, the imaginary part of some calculation, what about the Lamb shift, the real part? What about the Lamb shift? Does it go?
Can I ask a timely question here?
Yep, so I'm about to quit.
At that, okay, in the case of many...
So here's the answer. I've got a cylindrical configuration, okay. And this is now going back to the microtubules. And you see that when we have a couple hundred atoms, our eigenvalue for the decay rate is very large, in agreement with what we saw numerically and what our colleagues saw numerically. And here I'm looking at the effective Lamb shift. So the summary is that we study the two-dimensional structure over a period of a decade, and we find that things are working for us, that we can in fact compensate for coherence effects in biological or other systems by using the geometry of the cylindrical or spherical shell that we're working with. And I recommend that as a study for those of you who are bored some weekend. And at this point, I'm going to turn things over to my colleague, Dr. Yi, who was and is a hero on these important experiments that these guys are doing. And I will introduce him and I'll step away. Thank you for having me. I'm sorry I have to go to this meeting. Go ahead. Why don't you just come right in here?
I'm going to.
You can take off your mask.
Okay.
Okay, now, hello,
Yes.
this is Mehmet. You are gonna answer the question?
Well, hope maybe.
Yeah, okay, probably it will be easy for you. There is a single question at the moment by Zafer Gedik. It has been observed that drugs made from lithium-6 and lithium-7 have very different effects. Do you think that difference can be due to different vibration frequencies of the two isotopes rather than their different nuclear spins?
Yeah, I heard your question about lithium 6 versus lithium 7. We did look into the problem, not a little bit, but so far I indeed don't see much of experimental evidence in the literature, especially in the 80s, 70s, 80s. There are some investigations there, but I still, judge from the literature, I still don't see a very strong correlation. But the recent paper, there's one recent paper from Santa Barbara on this topic. I think that's interesting, and yeah, but we do need to look into more evidence there. But it's possible. Maybe spin. That's so far what I can answer.
Okay, thank you very much. Is there any further question from the audience? I'm waiting for them. Okay, but when they are typing, maybe I would like to tell something to you. First of all, we would like to thank you, Professor Scully. Even though he's coughing or his voice is not very good, he finished the talk. We thank you. We thank him very much. Also to you, and there is no question still. Actually, the end. One more thing that another comment I would like to share with you is that this was a very pedagogical talk, and even I could understand it. And last, we will kind of ask Professor Scully if it could stay in YouTube, and if Anatoly Barnabas is there, could you conduct my best wishes, and also Professor Sokolov and Olga and Zuberi?
Yeah, they are all around.
Oh, here, okay. Okay, is there any question from the audience? Otherwise, I will finish the session.
Okay, it's a great conference. Thank you for the invitation.
Yeah, we thank you very much, and have a nice day. I think the COVID there is not very effective because you are not wearing masks.
Oh, we actually do.
You do? Okay.
Yeah, it's just paradoxically he's attending another meeting, so yeah, he left the room. So
okay.
Okay. Yeah,
okay. Have a nice day.
But a lot of people already got vaccinated, so yeah.
Yeah, here only the 10% probably. Okay, thank you very much. And okay, I would like to announce that we have an evening meeting at 8:30. And just a moment, I want to read. Okay, Professor Hakan Türeci from Princeton University is going to give the talk entitled as Machine Learning with Quantum Dynamical Systems. So I give the microphone to Professor Ceyhun Bulutay.
Emre, thank you so much. So we look forward to Hakan Türeci's talk this evening. So please use the same link as you do right now. So see you all.